Okay, let's get started. Today, I'd like to welcome everyone to Trading Notes. Happy to have you here and for the conversation today. My name is Jack Murphy. I'm the executive editor of the Architects newspaper, and welcome. This week's discussion is titled Using the New AISC and ASCE Specifications for Sustainable and Resilient Structural Stainless Steel Design. So today we're going to learn about stainless steel's inherent strength, corrosion resistance, high recycled content, and performance under fire conditions make it an ideal choice for sustainable and resilient structural design. And the panel discussion that will follow will introduce publications. These publications I mentioned in the title present case studies illustrating their application and provide the perspectives of a producer, fabricator, engineer, and architect on their benefits in the design of structural stainless steel. And today's Trading Notes is brought to you by the Steel Institute of New York. Additionally, today's program will earn you one AIA learning unit and will be recorded for later viewing. Please allow 7 business days to process certificates of participation and for AIA credit reporting. And we encourage you to engage our speakers with your questions. So you can use the Q&A button found at the bottom of your Zoom window to ask questions. We'll kind of get to those and have a moment for response at the end of the program. I'm really happy and thankful to be joined by today's great panelists. You'll hear from kind of I believe in presentation order, Catherine Huska, who's president of Catherine Huska Consulting, Michael Mulhern, who's president of Tri-Pyramid Structures, Richard Green, principal of Green Facades. Ben Caldwell, principal of Green Facades as well. Mattia Del Giaco, CEO of Stainless Structurals America. And I'm here to moderate and to help with questions. So we have a lot to get through and a lot of exciting case studies and material. I'll turn it over to Catherine to begin today's program, and welcome to everyone to Trading Notes.
Thank you. Welcome to everyone in our audience. I'm so excited to talk about this topic. So I think it's important to point out that structural stainless steel has been used since stainless steel was invented, first for the industrial applications. The first large structural stainless steel applications globally were the gateway arch and the unisphere. The research that had to be done to build either one of these, but was started because of the gateway arch, became AISCE ASCE 8, which we'll talk about today. The gateway arch was the largest structural application in the world for 40 years. Then the Canadian National Archives were built, and they were the largest building framing application in the world. Not that there aren't others. There have been many different applications for structural stainless steel. I'm showing a few, and they provide well-documented long life. These are the documents we're talking about today. We started with the Design Guide 27, AISC. There's now a new version of it out. And once that was out, work began on the AISC specification for structural stainless steel in buildings and the Code of Standard Practice. Simultaneously, the AISCE ASCE 8 committee was organized. I was involved in all of these things. And I should mention with AISCE 8, it had been 20 years since it's been updated. It's been in the International Building Code since it was started, but it hadn't been touched. All of these now contain information about designing with duplex and highly alloyed austenitic stainless steels, in addition to the common stainless steels. And Michael, as chair of AISC 313, is going to talk a bit more about that experience. But I wanted to give you a bit of an overview as to why we're talking about sustainability and resilience. I'm very involved in ISO and ASTM sustainability and resilience standards. ASTM happens to be a bit ahead, but our government agencies and others around the world are all saying that we need both if we're going to reduce the carbon footprint and achieve our sustainability goals. If you look at 100-year projects or longer and consider material deterioration, replacement, repair, there's significant differences between materials. And when you have to do maintenance, you have to have an environmental impact. If you have replacements, there's an environmental impact, and all of that has to be considered in life cycle assessments. When it is, stainless steel has a clear advantage. I think it's also important to point out that there has been ongoing research globally on recycled content of stainless steels. There's published data out there from World Stainless. I'm showing the 2015 global numbers. There is a difference between those numbers and the US specific stainless steel production data. I've shown carbon footprint for 2015 versus 2019 to show you that there has been a significant reduction. The industry has worked very hard to reduce our carbon footprint. There are areas where, well, we need more sources of alternative energy, for example, to help reduce it further, as well as improved scrap availability. Oops, sorry. We are talking about resilience tied in with sustainability because the reality is that the resilient loss events are increasing and have been around the globe, whether they're human caused or natural, associated with global warming or otherwise. Stainless steel checks off all the boxes in terms of its incredible impact and blast resistance, its energy absorption, which makes it ideal for that and seismic applications, and its fire resistance. With that, I'm going to turn this over to Michael Mulhern, who's worked closely with me on AISC standards and other projects, and to talk a bit about how we got here.
Thanks, Catherine. My name is Michael Mulhern. I'm president of Tri-Pyramid Structures. For those of you who don't know us, we are a designer and manufacturer of custom architectural work around the world. Some of it's industrial, most of it's architectural. And I'm going to very, very rapidly talk about why we have these new codes. The picture on the screen right now, we've all seen it in one form or another. But that column on the left, in my view, has failed. It is within about 200 yards of this tower that we built on the right-hand photograph. Now the column is somewhat older, but we know that we can do better than this in carbon steel, but at the end of the day, carbon steel is going to rust and rot no matter how good a coating I put on it. So why do we have this new code? This illustration is a drawing I actually stole out of Modern Steel Construction. The author wouldn't let me use his original, so we redrafted it. But what you see here is a very typical drawing for the last 20 years. The stainless steel wind girt, 12 by 4 by 5/8 stainless steel, grade 36. There is no such thing. There is no such thing as stainless steel plate. There are 300 types of stainless steel. I'll come back to this drawing in a few minutes. What is it that separates stainless steel from carbon steel? The answer is that the stainless steel is much more ductile. And when we look at this graph on the bottom left of the screen right now, you'll see the green dashed line next or offset against the red line. The red line is what we call a stress strain curve for carbon steel. This is ubiquitous. You know, every engineer in the world saw this in their first year of engineering. What you see is a big straight line, and then once we get up towards something I call FY there, it goes off to the right, sort of horizontally, and goes plastic. Notice that the green line has got that big curve in it, and it isn't nearly as straight along what we call the elastic range. That's ductility. And in the austenitic stainless steels, they're ductile. What does that mean? They stretch a lot. They move a lot. And so it turns out when all these years we've been talking about using stainless steel with the same design parameters as carbon steel, it's wrong. It's wrong from the standpoint of the materials behave differently. And that's why we have the new standards. A lot of it is the same, but some of it's real different. And some of the equations are real different. So as a quick introduction, this is a talk, you know, I can give for many hours. So you're getting a very short version of it. As a quick introduction, you know, first of all, what is stainless steel? It is not simply non-rusting steel. It is a different material. And that top left-hand graphic, which shows you if we start at the center and add different types of alloying, we get a different metal. Those metals are not, they don't just behave differently. They are in many cases different at an atomic structure level. And we have this material we call austenitic stainless steel. It's different from carbon steel, which is a ferritic material. And there's a reason why when you put a magnet to a piece of austenitic stainless steel, it doesn't stick. It is non-magnetic, and that happens at the atomic level. The bottom of the screen, we're looking at what we call lateral torsional buckling, or what happens to this material when we twist it and bend it. And this behavior that you see on the right-hand photographs is different than it is in carbon steel. And the graph on the left illustrates that graphically, where you see the black line, and that's how carbon steel behaves. And you'll see that the stainless steels, both the duplex, the red line, and the austenitic, are real different, right? So a long way around, they're not the same. And that's why we have new codes. The other piece of this new code network is that there are plus or minus 300 stainless steel alloys grades available commercially. So the Outokumpu guide is, you know, it's thick. And there's all these tables about what stainless steel are available. And for a designer, this is incredibly intimidating. And what they don't tell you when you leave school is that most of these are not available to us. If you want to order a mill run, they're available. But for the most part, there are very few stainless steel alloys that get used all the time and are available in a number of sizes, a number of sections. So we've narrowed it down in the code committee so that you as practitioners have a list of things that are actually available, well, more or less available, and you have a potential of being able to put them in your project. Nothing is more frustrating to me as a fabricator than to have a drawing come along and say, I want to make this out of unobtainium stainless steel, and for me to have to spend the next 3 weeks explaining, no, I know what it says in the catalog, but we can't get it. So that's part of this effort. To give you a little more insight into what Catherine was explaining a second ago about what is the code landscape right now. For those of you who work in carbon steel, the Bible in carbon steel is AISC 360, the specification for steel buildings. So in carbon, that's the book we use. Has a lot of formulas. It's very big. It's at the back of your steel construction manual. As a family of design guides and as a family of codes, we also have a code of standard practice for steel buildings. And that tells the practitioners how we relate to each other. The structural engineer, what his job is, me as a fabricator, and there's a lot of rules in there. We took those two documents and we morphed them into the two new documents for stainless steel. AISC 370 is the specification. 313 is the code of standard practice. There's a lot of verbiage the same. There's a lot of verbiage that's different. As Catherine said, there is a new AISC 8, which is for small, thinner sections. And if you don't take much more out of my talk than this, the Design Guide 27, free online, is an enormous compendium of really important information about how we design in stainless steel. It's really a great book. So we're back to this drawing again, and I don't have enough time to explain it fully, but I'm going to point out a couple of things. This section at the bottom, which showed as a piece of tube steel before, doesn't exist in stainless steel. Our code now requires you, if it doesn't exist, to draw it the way it's going to be made, which is as a box section. And the code requires you to not write stainless steel. It requires you to write what kind of stainless steel. What finish do you want? And how are we going to, in what temper, how are we going to supply it? How are we going to finish it? One of the big new items, giant new item, is that in stainless steel, we do something different than in carbon steel. The first thing we are supposed to look at is corrosion resistance. Somebody's paying money to have this, either for resilience, for its long life, or for the aesthetic qualities of it. But the first element in stainless steel is it actually going to hold up in the environment we're putting it in? There's a whole lecture on that as well. As I told you, we tried to make life simpler. This list of available alloys is what's in the current specification. And down from 300, we're down to 21, of which only these ones that are yellow are commonly available. So there's like 10 alloys that are available in the code that you can normally buy. And we talk about that in the code and we say, look, here's what the code covers. As a practical matter, you can have all the codes in the world. Craftsmanship matters. This is the bean in Chicago. If you've never seen it, this is the finest piece of stainless steel metalwork that I know. And we make some pretty nice stuff at Tri-Pyramid. This is what we see every day. One of these pictures is from Catherine. The rest of them are from me. This is very common. It makes my heart bleed every time I see this. But craftsmanship, how you go about making stuff, is as important as whether you select the right material. That said, oh, my timer's going off. I'm done. So it's not hard to work with. It's kind of fun. And that's what I have to say about why we're doing the standards. Now Richard and Ben can show you what we do. Thank you. Catherine, you're muted.
Thank you, Michael. Thank you, Michael. Richard Green, I'm principal and founder of Green Facades. We specialize in doing facade systems on buildings, but some of those facade systems get pretty big. We enable architects through our engineering. So I wanted to start off by perhaps challenging some of those ideas of what is big in stainless steel and small at the same time. This is the Suvarnabhumi Bangkok International Airport, and it's 360,000 square feet of a glass enclosure, all sitting on stainless steel tension trusses.
Richard, we're not seeing your slides.
Yes.
We're not seeing slides yet. Oh, okay, hang on. One more button in team in, are we live? You see that now?
I can't see. Oh, there we are.
Yes?
Yep,
Yes.
just make it full screen. We're looking good. We can see it. There we go.
Great. All right, start again. I had a green bar around mine. All right, Bangkok Airport. So to give you an idea, this is 3,600 feet in perimeter, 100 feet tall. And it's all stainless steel tension trusses. Now, being all this truss work on the interior, we could have done this in steel, and it was actually originally specified in steel, but we changed it to stainless steel because we wanted to do this for a risk management. We were very late in the schedule when I was brought onto the project, and we looked at it and we just go, if we make this out of steel, if we make it out of fabrication, then we've got to send it off to paintworks, and the paintworks get delivered on site, and it's near the glass, and you've got to start repainting things next to the glass. It was just a potential disaster from a delivery schedule point of view. So we normally look at this from a corrosion point of view, but in this case, there are actually external, practical and financial drivers towards why we're using stainless steel in this project. And so the question is, why don't we just design it like steel? It's familiar, it's kind of like steel, but the yield curve, as Michael showed, is quite different. The Young's modulus, as you interpret, needs to be different, and it cold works. So as you start applying work on this material, you start pushing up that curve, it gains that strength because of the dislocations that end up in the network. So in this respect, rather than just going plastic in that horizontal platform, it's actually getting stronger as you work it. And this really does change it. There are also other practical aspects of this. So if you're going to do slip joints, that self-healing surface that forms a new oxide on the surface, if you rub things together, this can be as simple as a nut on a bolt, and you take that oxide layer off, it will reform those oxide layers, and if it forms it together, you're effectively cold welded your material. There are things which are considerations which you need to be thinking about when you're detailing, which are different to what you do in steel. So, how many formulas inside the steel design manual includes FY? And it's just about all of them. Somewhere in the process, everything designed comes around FY. And this idea of a yield plateau is entirely different shape when we start talking about stainless steels. So if we're looking at a common column arrangement, we can see we have the Euler buckling curve where it's fully elastic. We have the yield at the top, but the transition between the two of them is this inelastic buckling curve that allows for imperfections, allows for some bending, allows for some plastic movement. And that's the area where the materials behave really differently. So if we look at them side by side, we see on the left, this is our very familiar steel code for columns. And on the right-hand side, we see something which is familiar in format, but includes a number of additional parameters to allow us to fully utilize that space. Same as we transition with our shapes from elastic to plastic in beams, that inelastic region is really important. And again, the formulas look more complicated, but really they are something similar with these additional parameters which are material specific because the behavior of stainless steel is different. So let's just look at the other aspect of it. It's not just the material. When we look at it, the raw cost of the material does cost more, otherwise we'd use it all the time. But when you think about it in terms of finished cost versus the raw cost, the amount of value add that we have in there is very similar. And when we engineer things, that ratio of material cost to engineering cost to fabrication cost really does influence the techniques which we use inside the way we build things. So if you look at bridges that were designed in the 1930s, labor was relatively cheap. We see lots of lattice work and rivets. If we look at things which are now, labor's expensive, laser welders are cheap, you see lots of welded thick plate girders. It's just an expression of this ratio between material cost, how much time we spend engineering it, how much time we spend fabricating it. And so one of the big differences with stainless steel is because it costs more, we tend to do more refined designs. And so here is an example, again, Bangkok Airport. It was originally designed as this big cast iron knuckle, which would have been cheap. But now that we look at stainless steel, the fabrication techniques which are available with people that are working with that material allows for a much more refined design. We go through the process, we do elastic plastic analysis, we optimize the shape, we end up with much less material, And when you have much less material with the fabrication cost, this ended up being very favorable considering the risk profile and the cost profile. Now, before you have a good standards material specific, and Bangkok Airport existed before 370, we had to go through this process of justification, testing, engineering analysis, and judgment of what is appropriate. Now that we have standards in place, it allows us to free stream that much more efficiently and effectively. So Bangkok Airport was delivered not just because we had this aspirational material or an aspirational aesthetic, but because it allowed us to have one-stop shop with the fabrication. We didn't have to go from casting to machining to paint shop to risk of transportation to all of these other things. The overall risk analysis really made the project work to give us a quality project. And I think it's the largest glass enclosed volume anywhere in the world. It's basically the Boeing factory with a glass wall on it. And it's, you know, an amazing use of stainless steel. Now, this is perhaps more of what we think about in terms of, you know, structural formats. This is a lattice tower, and it's an art structure which is going around a industrial pumping station in a residential. So it's really an art piece around it, but it's 70 feet tall, 60 feet in diameter. And both Michael and Catherine have assisted in the development of this project, and it's currently out to bid, which is why I can't name it. But when we start looking at this, more expensive materials, thinner walls. When using thinner walls, you're more interested in the buckling profile, you're more interested in what's happening in that inelastic region. This is why the material specification becomes so important, is because that's where the materials behave differently. And this is where you get the efficiency of design, and this is what these standards allow you to do. So standards, you know, we spend more time optimizing. We spend more time getting special shapes. You know, Matt's going to talk about this. We're not just using rectangular sections with even profiles on all sides. We're optimizing things towards where we need the metal, where we get the benefit out of it, how we get that cost benefit. We circulate collective expert opinion on these things so that when you start designing, you're starting with something which is a roadmap that says, get yourself in the right place. Then you can get expert opinion on these other things, but you're able to design and not make structural mistakes. You know, it facilitates specification. When you're an architect or you're a designer, how do I get what I'm expecting? Well, if you're specifying to standards, you don't have to write this manual yourself to get what you expect. And the other side is when you're doing a special structure and the building department goes, oh my goodness, what is this thing you're designing with this material that I'm unfamiliar with? You can say, well, here it is. I've got it. And all these guys that are really smart and expert have written this book, and I'm following it. And this really helps you get through the building departments and avoid them saying, please do custom testing, which is very expensive. So I recommend all these standards to you, and we're going to hand over to Matt, who's going to tell you more about these wonderful shapes and finishes.
Thank you, Richard. And Matt, we can't wait to hear from the manufacturer.
All right. Thank you, Richard. Thank you, Catherine. Let me just share my screen with you guys. Matilda Jaco from Stainless Structures. We are a manufacturer of laser welded stainless steel profiles and shape. I think as a starting point, I'd like to mention that when designing with stainless steel, it's very important to reference to the right standard. From this point of view, the new STM 484, on which Catherine did an incredible job to widen the scope, is covering most of the thing you need when it comes to general requirements for stainless steel bars, billet, and forgings. In particular, you will find very interesting, the tables covering hot rolled and extruded shapes up to 8 inches of size. That's because that's a typical range of productivity of those sections. You will not find in USA or in Europe or even in Asia any hot rolling facility or extruding facility for stainless steel, which can go wider than 8 inches or maximum 10 inches sometimes. When you go to bigger sections, at the point ASTM 484 is going to point you at the 1069. 1069 has been the ASTM standard of reference for the last couple of decades regarding laser welded sections. It's very important to specify the standards because they don't only mention chemical and mechanical properties, but also the qualification routes and the dimensional tolerances. I mentioned a couple of technologies such as hot rolling, extrusion, laser welding. I would like now to show them to you in a plot where you can see on the axis aesthetics and design freedom. Because, as a designer or architect, you might want to have certain, creativity in your projects. You can see how while hot rolling is very limiting in terms of, creativity, and also does not provide a very pleasant visual aspect due to the process, laser welding definitely can help you with that because it gives you a lot of design freedom while offering also, a good surface, almost invisible welds, and, a pleasant appearance. In this slide, you can see a comparison between two channels. On the left, you have a hot rolled or extruded channels. On the right, you have a laser welded channel. The main difference are highlighted by the orange dashed areas. You can see, for example, the hot roll channel has taper flanges and round edges versus a laser welded channel with crisply sharp corners and straight edges. In addition to that, you can see also the surface is different. The hot rolling or extruded process, they usually have rolling marks or superficial defects. It's just the nature of the technology and the process. While laser welded shape can give you a pristine, clean, white blasted surface. Just to give you an idea of how laser welding compares to conventional welding, laser welding can offer you a monolithic structure characterized by the same mechanical and chemical properties than the parent material used, and this is very beneficial to designer engineers because you don't need to use a welding correcting factor because the material you use is now a monolithic structure. So it's, from a mechanical standpoint, is equivalent to an extruded shape. However, you gain in flexibility of design and in surface appearance, and it's typically conforming to the AISS guidelines. So for architecturally exposed steel structures. This superficial finishing also help to add additional options in terms of finishing, such as polishing. There can be number 4 finish, non-directionals, number 6 finish, a mirror finish. And a good example of that is a recent project we've done for the Ars Sonora of the Tampa Bay University, where laser welded sections, polish number 6, were used for their bell tower. As designer or engineer or architects, you can stress the importance of the sustainability and resilience of this of your choices, or the shape of choices, in different ways. With the design, choosing the right suppliers, and selecting or specifying the right standards. When we talk about design, for example, there is a way to save material. If you go for a more flexible technology, such as laser welding, for example, you can, for example, specify different wall thicknesses. In this way, you avoid over-engineering and you save material. On the other side, you can also try to create sections with certain functionalities. For example, you can have some area of your section, maybe the one exposed to a more aggressive environment with a higher grade, and another area of their section using lower grades. A good example of that is this product we manufacture for the Coors Miller Brewery, where we could use a duplex stainless steel 2205 rail as a welded to a T section. In this way, in 304 steel. In this way, the customer could benefit from let's say, cheaper solution for the T-shape with the 304 stainless steel, whereas it could have a higher grade 2205 stainless steel for the round bar rail, where it needed higher corrosion resistance and mechanical properties. As I mentioned, using the right standards is very important, also for the sustainability and resilience standpoint. In particular, if you use the STM 1069 or the STM A1127 standards, this will allow you to have standards that are completely aligned to the carbon steel equivalents. So we're going to have tolerances, we're going to have mechanical testing requirements, we're going to have inspection requirements, and in this particular example of the 1069, you're going to also have mechanical properties that are higher than the one specified for the raw material. Typically about 15% higher, which also give you a good benefit in terms of, avoid over-engineering. Last but not least, from the point of view of sustainability, is the selection of the right supplier. There are many suppliers who are involved deeply in having sustainable projects, sustainable cycles, and Steel Structurals for sure belong to this group. Today, we can go on the market with what we define green structurals, because we can produce our laser welded shapes only using clean energy. Thanks to our 4,000 panels solar system, which is about the size of 2 football fields, we can now go on the market starting from highly recycled raw material, such as the one provided by Outokumpu or North American Stainless Steel, which can have a recycled content up to 85 or even more %. Using green energy, we can really have a near to net zero carbon footprint structurals, and that's very important if you want to have structures and design characterized by sustainability and resilience. I can now give the word to Ben.
Yes, and I did want to mention, since with some of the projects Ben's going to talk about, that Matt is also affiliated with Montanstall, since you're talking about 7 World Trade Center.
7 World Trade. Absolutely. Hello, all. Ben Caldwell. I'm an architect and specification writer at Skidmore, Owens & Merrill. And I get the fun part. Thank you, everybody, for the standards and for the work you do making beautiful buildings. And we get to then we all get to enjoy them in our city. Tower 7. This was the first tower after 9/11. Next. And it was very important that the first tower after 9/11 become a beautiful, crisp, and permanent looking building, so that obviously structural stainless steel was a very natural choice. Next. This is our 20-year-old rendering of the building. Next. This is what it looks like yesterday from a photo. We love structural stainless steel. The lobby 20 years ago, rendering the next. The lobby is still as beautiful today as when it was built. Next. Yep. So the structural stainless steel allows us to make beautiful details that we know will be as beautiful today as they were when we built them. Minimal, precise. Thank you. Beautiful. Next. We're moving uptown. 10 years later, SOM designed a building at 250 West 55th Street. This is, again, a very simple, elegant building. Wanted to make a very nice, crisp street presence with a lobby, image, and rendering. Michael, thank you for this. This is beautiful. You did a great job. Look at that. We have unbelievable 3-story tall stainless steel mullions that are as crisp and straight as we could have imagined. Thank you.
Enjoyed it.
You know, minimal work on the revolving doors. Next. And just you know, the appearance of these structural stainless steel mullions from the outside are probably better than what we had hoped they would look like. And again, because of the strength of the stainless steel and the finish that we were able to get. Moving further uptown, and then we'll go back another 10 years, back to 2004. This is the project, the Time Warner building, now the Deutsche Bank Center. This is next. Again, an example of an amazing entrance and lobby that we're able to make with structural stainless steel. The entrance canopy is obviously restraining then a huge cable net facade. Next. With that minimal cable net, we're able to do that with the structural stainless steel. Next. Here's a detail from around the corner in a smaller cable net facade from the same building, but it just, I have the pleasure of getting to walk past this every day. You know, it brightens my morning and it brightens my evening seeing these amazingly crafted stainless steel details. Next, and then of course the experience from inside the store is as good as we could have possibly hoped. The shopping lobby, you find people in here just hanging out. So thank you, stainless steel. Next, we are now 2024. We've just completed this entrance canopy to Penn Station, to the Long Island Railroad. You no longer have to walk down some dark stairs underneath Madison Square Garden. Next. So awful lot like the rendering. Next. So rendering for the for what this was going to look like, and next. This is how it turned out. Again, thank you, stainless steel. Next, rendering. Next. The real thing. I think the real thing is actually better than the rendering. This is a beautiful stainless steel cable net structure that we've got over the canopy. Next. So quick overview, the design attributes of structural stainless steel. Next. So we've talked about it a bit already, but that it is naturally beautiful as is. Matteo and I have talked about this already. I don't think there are very few things where we actually keep samples on our desk because they're just so beautiful. But these are stainless steel connections that and products I keep on my desk. They're just so beautiful. Next. And the sustainability aspect that we've talked about is it's a beautiful, hard, low maintenance surface with a very low risk of damage. We have no additional finishes needed. There's none of the VOC concerns of paint, none of the VOC concerns of anodizing. Any refinishing that is required is just elbow grease. That's very low VOC. Next. So I actually keep this. I keep a Scotch-Brite pad and a little piece of stainless steel on my desk, so that when we're talking about how to refinish stainless steel, we can refinish it very easily. And I love that about stainless steel. Next. So so after refinishing, it's stainless steel. With we obviously have to use the right alloy to make it truly stainless, but it is also it's stainless and salt resistant, and we'll call it urban liquid resistant. Next, an extremely long life. We're now talking about 200-year buildings And so stainless steel is just is such a nice choice for it. Structural stainless steel, highly recyclable at the end of the life eventually. Next. We're also using a smaller case, smaller applications, but it has a low thermal transmission other than aluminum as an example. So we're often using it in lieu of other material. And next. And as Catherine's already pointed out, non-combustible. We like non-combustible. Thank you.
Thank you, everyone. Since I only see one question from the audience so far, I'm going to throw out one to get some discussion started while our audience posts a few more questions. Ben, I'm not sure if everyone in our audience realizes how innovative SOM has been over the years. In the 7 World Trade Center, we had some tremendous resilience challenges. It was the first building in the world to use 2205 for glass curtain wall. How will these new standards change your job?
Well, we can now use the product with much more confidence, knowing that we're not going to be delayed in the engineering and in the building department, because I think like Richard said that you know there's not going to be the hands thrown in the air. What's the standard for this? Now with this new standard, with the new standards, there's a piece of paper to back up these selections of the material. So thank you for doing that.
Okay, thank you. We have a question related to embedded carbon steel, and I was thinking, Michael, would you like to comment on that?
Well, yes. So the question really is around what do we do, we quantify. We can't change the embedded carbon a whole lot. I mean, to be blunt, it is what it is in the material. To quantify it over the last really 5 years, all of our manufacturers have taken on telling us what the embedded carbon values are. It's a much bigger question to ask, how do you lower it? And it's really not for this forum, but it really has to do with energy input and stuff like what Mateo are doing at Stainless Structurals, and using solar power and other power to generate the power that goes into the manufacturing. Things like moving plants to be closer to the wind farms or all the rest, not particularly beneficial because you're robbing Peter to pay Paul. But when you actually add generation on a site, that's a different matter, because now we are reducing the embedded carbon. I hope that's helpful.
Yes, I think so. There's a question about cost and how that often stainless steel ends up being taken out of projects. I recall, Richard, that you did a significant cost analysis for the Bangkok airport. Perhaps you'd want to comment about that?
Yeah, when you start saying I've got this section and you compare it with a like section that's not actually fully optimized, then yeah, it does cost more. And the question is, in a value engineering sense, are you talking about first cost, or are you talking about lifetime cost? I think the graph that you had there, Catherine, about what is maintenance, what does it take to repaint or do maintenance? And I've got a project at the moment where they want to do the substitution, and you just realize that it's completely impractical to actually pull this thing apart to get to the places you'd have to get to actually repaint and recoat. So there are times and places where the initial cost, you look at it and go, yeah, it looks like X amount of pounds and X amount of pounds, it costs more, for sure. It's true. But then you need to start thinking about what is the final evaluated optimized cost. I've got a standard size versus an optimized size. I've got painting and surface finishing, then I've got a maintenance cycle, then I've got a site risk, then I've got multiple trades and schedule risk associated with site damage. A lot of things come into the total equation, which rarely gets included in that initial cost appraisal. And so when you start going to what is a cheaper solution or reliant on high performance coatings, you end up with that yellow balustrade baluster that you had column base. So I think a lot depends on the client, but I think a lot also depends on us as designers to think about the more complete picture rather than just this initial first take on it.
Yeah, I'd like to quickly add, Catherine, to pile on with Richard, is that we think of cost as money, but and it's not just that upfront money. It's the cost to to society to have to replace that product every X years versus X times 3 years. That's another cost that we really have to start taking that into account more than we do.
Yeah. Absolutely. I see a question about resilience, and I think that we're going to get different perspectives on that from this group. And I did notice a comment that I think might be from a mutual friend. Christopher Olson might have posted this. Ben, maybe you might want to, since he mentioned Seven World Trade Center, you might want to jump in, but I'm sure others have some thoughts about resilient design. Okay.
I think Marty also said he was interested in responding to that.
Yes. I know for Seven World Trade Center, energy absorption, fire, were all big considerations. But I'm not sure how much you can say about that.
So, Catherine, I can bring an example right to the fore. We did a project in Washington, D.C. for a government building where we did what we colloquially call crap catcher. So behind a big curtain wall, there are stainless steel tension elements that are meant to catch the wall should a blast occur. And in the end, we went to a medium strength stainless steel product that has an enormous amount of energy absorption capacity as it yields, understanding that it wasn't going to come back to exactly its same shape when we were all done. But using the top part of the yield curve and saying, right, here comes the wall, we're going to stretch it, but we know that this material won't fail before we've absorbed all the energy of not just the blast, but the blast times quite a lot, because you actually never know how much fertilizer the person's bringing in their truck. And I say that jokingly, but it's no joke. One of my big things about resilient design is it's not about the level. It's about what happens when we exceed the level, and what actually is the failure mechanism look like. Is it going to be soft and subtle, or am I going to have a major failure? When you look at adding more concrete, once the concrete fails, it's coming into the space. And typically, if you have a material that has a lot of elasticity, yeah, it goes a little further into space, but it still slumps onto the floor. So we think it's great for that.
Matt, I have seen some of your videos where you turn I-beams, totally flatten them, and the welds don't break. So I thought you might want to comment on this.
Yes, we did that. That's our, I can say, crash test without any number. It's very impactful to the people who witness that. I mean, there is no stress strain curve or any data, but you can see how, when applying 200-300 tons of pressure, the weld doesn't break. And we did that several times for, different application, from blasting resistant walls, both with stainless steel or carbon grades, to, fabricators who wants to have, some parts laser welded and not sure, if it's strong enough compared to an extruded material. And, and sometimes very hard to demonstrate the tensile or the bend properties on a fabricated part. So the best way to show it is just to do a little mock-up and to crash it and see what happens. So typically it goes a long way with engineers and designers to see that, even under such a strong pressure, the weld resists. Of course, in addition to that, we do normal mechanical testing, more according to engineering guidelines, so a proper dog bone tensile test. We typically see that, the breakage happen in the raw material rather than in the weld. The weld process, the laser welding process, has this great advantage that when the material resolidify, it's very dendritic, so very oriented, and this give very good properties in terms, tensile and bend resistance, typically exceeding, the parent material. And we've seen this both with, the common austenitic grades, 304, 316, but also with the 2205 duplex stainless steel.
Jack, did you want to
Yeah,
wrap up?
I think this has been super informative, and I like the conversation and discussions. There's a question in here about ebonized finishes, and that's kind of interesting to me to think about visually, beyond grain and other like properties of the metal, like what kind of finishes are available if you're designing in stainless.
I suspect I'm probably the best person to answer that when I did see it. So there are several ways you can darken the finish of stainless steel. The absolute worst way is to expose it to heat, because you reduce the corrosion resistance of the stainless steel dramatically. It's been done. It's a horrible idea, because you're undermining the corrosion resistance. Electrochemical colored stainless steel, as well as PVD coatings on stainless steel, are probably the best way to get a darker appearance, but they do have some limitations, including, the sizes that can be colored. I strongly discourage in an exterior environment using things like the blackening that's used for gun barrels, and actually the chemicals that are used on carbon steel to do that are completely wrong for stainless steel. I mean, there are separate ones for stainless, but it will not hold up well outside. So there are some options, and AMOA's website does have an entire page on that topic. So did I miss any more questions?
I also think, I mean, there's one just about general lessons learned and kind of rules of thumb, and that's a very open-ended one, but I'm curious if there, from the experts that we've gathered here today, if there's, any things to keep in mind, or, any tips that they might want to share.
Michael, you haven't talked that much about your projects. Do you want to jump in on that one?
Honestly, I don't know where to start. There are so many lessons learned and so many. What I'm going to say is, number one, if you go to our website and look at the body of work that we have, tripyramid.com, and look at the projects, you will see an enormous number of stainless steel elements used in different applications, different places. And I think the biggest lesson, and this is odd to say, but I'm going to say it, the biggest lesson that we've learned over 35 years is, frankly, to pay attention to the designers and our clients who have some pretty crazy ideas, but we've built a lot of stuff that we didn't think was possible by virtue of being pushed a little bit by our clients. and I'm going to say something that is going to make Catherine cringe and the code committee cringe. We have at times been forced into doing things that are outside of what I helped write into the code. It's possible. It can be done. There's a lot of creativity. The code is really, really important. It allows us to do bog standard things. But one of the lessons that we learned from some fantastic projects, some of them are very large and you'll recognize them, is we can get past that collectively. We're engineers can. This is not the end of the story. So I know it's not exactly the answer that AMOA wants to hear or the code committee wants to hear, but it really is true that there's a lot can be done inside and outside of the code.
I think you make an
Richard.
important point there. Oh, you're about to ask me about that one. Exactly.
Well, yes, I could see that you wanted to jump in.
Yeah, I mean, we've got to remember that standards are for standard structures. And a lot of things we do with stainless are not standard. And so it's a two-edged sword. On one hand, it gives you, I like to think of it as you're starting at third base rather than starting at first base, right? And that final process, you've got to say, is what I'm doing, does the standard cover this? If I'm outside of what it was intended to cover, the guidance in there may not actually be applicable. And secondly, you've got to realize that sometimes those criteria which are written there are applicable for many cases which may not be applicable to your case, in which case you can ignore it. So it's one of those things which you've got to treat standards as these were written with as many examples as possible, but they're not 100%. And we can never say, oh, I followed the standard, therefore I can ignore everything else I know in the world or anything else I could deliver. You've still got to be a thinking engineer about it. And conversely, there are possibilities by going beyond it. And so this is how we make these amazing things happen.
And Catherine, if I could say one other thing about that, I wasn't joking or self-serving at the end of my slide deck about craftsmanship matters. Who you choose to have be your engineer, I mean, that's a craft. Who you choose to make this stuff, it really does matter. You know, I don't care. The code in the hands of somebody who is not trying to do good work isn't going to help you. I'm going to just be blunt. And so as practitioners, we owe it to our clients to do that. I believe it's a duty of care, particularly using materials that aren't every day.
Absolutely. Ben, since you've been involved in a few projects pushing the envelope, would you like to comment?
Well, my comment would be this is why we have experts that we associate with. I mean, I'll probably get myself in trouble with a lot of the architects. We are rarely masters of everything, but we are often masters of finding the right people to work with. And to be honest, now I'm just embarrassed myself, which is when you, Catherine, when you and Michael asked me to be on this panel, I was a little dumbfounded that I could, you know, to be with the two of you is pretty remarkable. So we push the envelope because we can, because we know we have people like you and Michael and Richard and Matteo to build these things that we've designed. And you like doing it. That's why we do. It's what we do. It's why we're doing this. There's nothing better than having a project that's finished, turns out kind of like you thought it was going to. You go there with your family. Your buttons are bursting on the front of your shirt. It's pretty great.
So,
sorry,
Matt,
a little corny,
okay.
but
Yeah. Well, and I know you well enough to know that's exactly how you look at it. But I mean, it's a lot of fun to work with an architect who has a great concept, and we just have to figure out how to make it happen. And Matt, you must have a comment about this.
Yeah. Yeah. You know, that's why I made the graph creativity and aesthetic, and see how the technology can position there, because, you know, I mean, our company mission is to, you know, to provide great products, of course, great customer experience. But I think bottom line, we want to serve the ingenuity of the engineers and the architects. You know, they have great ideas and the great design, and we want to be there to help them. You know, not to compromise. If they have an idea, to be able to find a partner, a supplier that can make that idea become reality. And it's not so obvious because, you know, the stainless steel market, it's 90% standard shapes. You don't go very far with those. I mean, if you want to have, you know, the level of engineering and design that, you know, Ben, Richard, and Michael show, you need to have suppliers that can work with those ideas, they can make it happen, they're willing to take challenges. You know, but very often we do projects that they are at our limit. You know, we push the envelope to get there, but we're happy to do it because eventually, as Ben underlined, then you can be proud, you know, of being part of something that is there for everybody. It's a treasure. You know, it's something that you want to treasure. It's something that everybody working in New York City can admire every day. And even if you're just a little piece of the puzzle, you need to be proud of it.
Well, thank you. I think that all of this illustrates how important it is to make sure that whoever you are working with does their homework, knows what they're doing, and even if it might be newer to them, they've clearly gone through all the steps necessary to provide the best product possible, to make sure they understand stainless steel, the different stainless steels, and aren't just making assumptions like it's carbon steel.
That's, I think, a great place to wrap up. I know there's been a lot of expertise, you know, shared today. It's really exciting to see these updates. And, you know, I think if guests, participants have further questions, they can seek you out or, you know, be able to engage these experts to learn more. So I just want to say thank you to everyone for attending. Today's trading notes under the heading of using the new AISC and ASCE specifications for sustainable and resilient structural stainless steel design. This session has been recorded. I know there was a question about replaying or slides. If you can use the same registration link to replay this edition of trading notes. And if you're in search of credits, please allow 7 business days to process certificates of participation and AIA credit reporting. I'd really like to say a big thank you again to the Steel Institute of New York for sponsoring today's trading notes. And finally, a big thank you to our presenters who made time during their busy days to share their expertise in dealing with this resilient material. So thank you, everyone. We hope to see you all again at a future event, and have a great day. Talk to you soon.
Thank you.
Thank
you, guys.
you.
Thanks, everybody.
Bye,
care,
everybody.
Everybody.